This is the April Geology News 2022. I'm Andrew Dunning, a graduate student at Portland State University, and I've been doing this segment for a while now. And I always have fun finding out what's going on around this ever-changing planet of ours. The fact that our planet is always changing is one of the things I love most about it. And I'm going to start out, as I always do, with earthquakes. The biggest event over the last month was a magnitude 7 out in New Caledonia here in the South Pacific. It's a very seismically active part of the world. This happened near the subduction zone plate margin out there. There's a couple of microplates whose names I don't remember at this time. I have not seen reports of serious damage from that area, which is good, or tsunamis or anything of that sort. So it's good when earthquakes happen and don't do much. Same cannot be said for some of the other ones around the world this month, unfortunately. There was a magnitude 6.7 in Nicaragua, which has caused some minor damage. No reports of fatalities that I've seen, but it's always a thing to be aware of that happens in some parts of the world in crustal earthquakes like that. A 6.7 is a good size shaker. And in Bosnia, in Eastern Europe, there was a magnitude 5.7, which has caused substantial damage to the common masonry structures of that part of the world. And there has been at least one fatality that has been reported so far. And that is, of course, deeply unfortunate, but not unexpected for earthquakes in this part of the world. Zooming into the US, this is a map of all of the earthquakes in the United States for the last 30 days. This is, again, as usual, sort of standard background seismicity. The largest event was a magnitude 5.1 way off the coast of Oregon here in the Blanco fracture zone. And the largest one onshore was a magnitude 4.6 out here in West Texas, which is related to the ongoing hydraulic fracturing and deep wastewater disposal here in the Reeves gas field. This is a map I grabbed off the Pacific Northwest Seismic Network showing the seismicity for Oregon over the last month. And there have been earthquake swarms around Mount St. Helens, Mount Rainier just to the north off the map, and down here at Newberry Volcano. And that actually prompted a Cascade Volcano Observatory activity alert email, which is kind of cool. Don't get to see those too often. This swarm was a little bit bigger than normal, but it was centered sort of deep below the volcano, and I'll talk about that more. Whoops, that's not supposed to be there. Hold on, Kitty is sitting on the keyboard.
The cat. What's the cat's name?
It's Ella.
Ella. Welcome, Ella.
Okay, volcanoes. So right now there are 42 ongoing or new eruptions around the world, or including minor unrest or activity. There has been substantial activity at Anak Krakatoa, Fuego, Nevado del Ruiz in South America, and Karimsky on the Kamchatka Peninsula. There's also some Alaska Volcano Observatory alerts for Pavlov, Great Sitkin, and another one, which actually doesn't show up on this map for some reason, of ongoing earthquake swarms in some of those Aleutian volcanoes. Now, about that Newberry volcano earthquake swarm, this here is a plot of all recorded earthquakes at the volcano since the year 2001, which I've hidden here cleverly underneath the inset map. But the y-axis is depth, so we can see how many earthquakes are occurring at which depth over time. Now this here is altitude 0, this is sea level. And so there's a good amount of earthquakes, these are very, very small. Some of them are even negative magnitude, which you can get because magnitude is a logarithmic scale. But most recently, this is our current earthquake swarm, and it occurred from really 2 kilometers down up to approaching the surface, not quite inside the volcano, but getting close, certainly in the volcanic system. And this is almost certainly just related to fluids and fracturing and stuff that volcanoes do over time. There's certainly no reason to expect an imminent eruption at this location, or magma movement for that matter. And as you can see, they're all occurring roughly underneath Paulina Lake, which is where the most recent eruptions at Newberry volcano have happened. That big obsidian flow, which starts right here, and this cinder cone whose name I forget at this moment. All right, I'm going to jump into some research now. Some new stuff has come out. And this last week, I was presenting my research, which I briefly mentioned, at the Seismologic Society of America meeting, which was in Bellevue, Washington this year. I was there all week and I didn't get home until quite late last night. But it is a global conference of seismologists. The America part of their name is sort of a misnomer. There were about 750 seismologists from all around the world convening to talk about earthquakes. And this is the first meeting since 2019 for obvious reasons, and there was a lot of new research, posters and talks and presentations on important global earthquakes like Ridgecrest from a few years ago, from the Sparta earthquake in North Carolina, which was actually very interesting, and of course many of the dozens of others that have occurred in the last few years. A lot of the research, apart from those, was concerned induced seismicity from things like hydraulic fracturing, the future of earthquake detections, which apparently people are using fiber optic cables to detect earthquakes, which is fascinating because the Earth is crisscrossed with fiber optic cables, and hazard modeling. There's been some, the USGS, for example, is working on updating their model of hazard and building damage that they produce after every major earthquake. A lot of cool stuff there. And of course, I presented my strawberry fault research. That was a lot of fun, short 12-minute talk, and you can learn more about that on the upcoming field trip. Now, just a couple of research items this month because of the other speaker we have coming up. One of the things that caught my eye was this oldest evidence of plate tectonics. Researchers recovered some zircon crystals from South Africa in the, there's a greenstone belt down there that dates back to 3.8 billion years, some of the oldest rocks on the planet. And these zircon crystals contained geochemical traces of subduction and alteration from pressure at depth. And this reflects a significant change in the behavior of the crust at the time, because the crust became destabilized at this point about 3.8 billion years ago. And this is the oldest confirmed evidence of plate subduction. And this sort of incomprehensible figure, I don't even remember what these the y-axes are. This is a little bit outside of my area of knowledge, but this down here is the ratio of uranium to niobium and their age on the x-axis, and that shows, I mean, that's used as a proxy for understanding the movement of a rock as it moves through the earth, including down to the mantle and in the crust. And I don't remember the exact details of this figure, but it does reflect right about here. We have this area of crossover between mantle-derived rocks and crust-derived rocks. So this zone here is evidence of old plate subduction, which is really neat. And another thing that caught my eye, which is something that I and most other plate tectonics enthusiasts have puzzled over for decades, is this mysterious bend in the Hawaiian seamount chain. If you look at a map of seamounts in the Pacific extending northwest from Hawaii, it kind of looks like this. Now, plates usually only move in more or less a straight line, and the Hawaiian hotspot has stayed in one place. And so as the plate moves over it, it leaves a chain of volcanoes and underwater mountains. But there's a big bend in this one, and no one ever really figured it out. But some supercomputer modeling that some scientists have done has refined the kinematic reconstructions for the movement of the Pacific plate over the last 50 million years. And about 30 million years ago, their kinematic model showed a 35-degree shift in plate motion, which tracks with the size of the bend in the seamount chain. And this is related to slab pull in the Kamchatka Kronotsky subduction zone, which is off the coast of Russia by the Kamchatka Peninsula. And slab pull is when the Pacific plate is cold rock, it's subducting underneath the continent or warmer oceanic crust. And as it subducts, It's a big lump of dense cold rock that literally tugs the rest of the Pacific plate down along with it. And some complex relationships between slab pull and push and other complicated oceanic crust tectonic stuff caused this bend in motion about 30 million years ago, which effectively explains the bend in the seamount chain, which is very interesting. And sorry for it being so short this month, but that's all I have for today. Thank you very much for listening. I'm happy to take any questions you may have.
Big wow on that explanation for the bend in the Emperor Seamount chain, because that's been a fundamental question for a long time.
Yeah.
How do we know that the hotspot has stayed in place? We make that assumption, but
so technically we don't.
okay.
And perhaps wandering of that hotspot plume has been considered as an explanation for the bend. One of the reasons that doesn't seem too likely is because the spacing between these volcanic centers is pretty consistent. And if it had started to move, you would expect the spacing to be a little bit different as it moves relative to the plate. So we always figured it probably had something to do with the Pacific plate just suddenly shifting. But this computer model showed that to be more or less basically what happened as a result of these subduction physics. And it does track with a known global reorganization of plates about 40 million years ago. So this shift took place over quite a bit of time.
Did it have impact
Andrew?
on, okay, someone go ahead.
Andrew, I was just wondering, you went through all the earthquakes, and there was one in Bosnia where there was a fatality. How did that compare in magnitude to the spring break quake we had down in Mount Angel in the size of quake? Do you remember what that was?
I think it's about similar. I don't remember how big the Mount Angel quake was off the top of my head. I think it was a 5.8 or 9. So yeah, it was comparable in shaking intensity. And that fatality was caused by someone running out of their building. So, if you're an earthquake strikes and you're indoors, stay indoors. Otherwise, something will fall on you and kill you. That's the biggest cause of fatalities in earthquakes.
That is good to remember. Les, do you have a follow-up there, or?
Well, a follow-up to what Andrew just said was I live in an old, nearly 100-year-old building downtown, and I for sure thought it was on the URM list that Portland issued a few years ago, and we had
Unreinforced masonry.
Yeah, unreinforced masonry, and all these buildings were supposed to put up plaques saying this building is in great danger if there's a big earthquake. And it turns out that my building, even though it looks like it's a brick building, is not. It's one of the first reinforced masonry buildings in Portland, and I'm living on the top floor. So I'm taking the takeaway from what Andrew said is I should just stay put here on the top floor of my building, or maybe go up on the roof. What do you think about that?
Well, since it's really difficult to predict where structures might fail, and even in those masonry buildings, the biggest hazard is not a building collapse, but the walls of the unreinforced masonry bend as the building shakes, and usually they just peel off like a banana peel. If you're in an older building and the ceiling is plaster, trying to walk around and get up to the roof would expose you to the hazard of falling chunks of ceiling or broken glass from any transom windows that you might have. It's best to stay put until the shaking stops.
Okay.
Is the bottom
Follow-up. We have a follow-up earthquake question from Nancy. If you don't address the earthquake swarms in the Azores, can you comment on them?
Oh yeah, I addressed those last month. There hasn't been any updates there. The earthquake swarm has slowed down a bit. So certain less than reputable internet sources have been saying that it is the precursor to a substantial, significant eruption in the Azores, like we have seen on one of the other islands in the Azores. I don't remember what it's called offhand, which a few months ago did significant damage, and I think lava destroyed 5,000 buildings and displaced thousands and thousands of people. So certain less than reputable sources are saying that this earthquake swarm means that's going to happen on this other island, which is technically possible. But these earthquakes are occurring at depth, so magma is not yet to the surface. It could very well be magma moving, but it's not yet at the surface in a way that we can say an eruption is imminent.
Okay. You mentioned that fiber optics are being used now as sensors. Can you explain the physics of that?
No.
No.
During an earthquake, seismic waves either dilate or contract the cable. I guess that's detectable in the pulses of light that pass through these fiber optics.
I see. So they're physically stretching the fiber
very minutely.
Okay.
Same thing with there's some lateral
Okay.
shear as well, but that's all detectable in the way that the light pulses are refracted.
That makes sense.
Fascinating stuff. I don't understand it.
Another question from the chat. I think many of us are wondering, Andrew, when you do graduate, what do you plan to do after graduation?
Don't ask.
Don't ask. All right. Well, that's a fair answer to that question.
I'll confront that when I get there.
That's very wise, I think. Well, Andrew, thank you. If there are no more questions, I think we can move on to Paul's presentation. And Andrew, as always, you're free to go at 1 o'clock, but if you want to stick around, if people have more questions for you, please feel free to do that.
Thank
So
you,
Paul, whenever you're ready. Thank you, Andrew.
Okay, let me share my screen.
And we're seeing your screen.
Okay, shall I start?
Please do.
Okay, thank you, everyone. I'm Paul Shea, and I'm a relatively new member here. And thanks to Paul for inviting me to give a presentation here. So I'm retired now, but before I retired, I worked as a groundwater hydrologist for the US Geological Survey in Menlo Park in California. And most of my work had to do with water resources, but groundwater is so ubiquitous in the subsurface that you inevitably can get involved with my colleagues' work. So I had lots of opportunities to kind of get involved with interesting geologic problems. So I'd like to share one experience, which is some of the stuff I did during the Kilauea eruption in 2018. So Kilauea is on the Big Island of Hawaii. And the Big Island is actually made up of 5 volcanoes, and Kilauea being the one furthest to the south. And actually it's not a very prominent volcano, much dwarfed by its neighbor Mauna Loa, but it's been very active. So the main features of Kilauea is a summit caldera, and then 2 rift zones, which are shown in this next picture, which is this area here. So here's the Kilauea caldera. There's this east rift zone and a southwest rift zone. And eruptions can occur all along these rift zones. And in the last maybe 40 years, most eruptions have been actually on the rift zones. This pink area is lava flows that has basically been going on from 1983 to 2018. And then the eruption that started in May 2018 was actually in this lower part of the rift zones over here. So here's a photo of the summit caldera. The caldera wall is actually this further wall out here. And then inside the caldera, there is a crater pit called Helebaumau. And then in the crater pit is this top opening of the volcanic conduit. And you could see a little bit of magma in here that's glowing red. And the magma level kind of goes up and down, sometimes spills into the caldera floor, and this dark patch here is probably a recent overflow that spilled lava into the caldera floor. So the plumbing of Kilauea goes kind of all throughout the East Rift Zone. So here's the caldera, and this region here is the East Rift Zone. And there are various crater pits and fractures, and any of these can erupt. So prior to the eruption of May 2018, most of the lava was flowing out at this Pu'u'o'o vent here. And then in May 2018, fractures opened up in this lower part of the East Rift Zone, and lava starts flowing out of here. And because of that, the lava lake in Kilauea started to drop, and also the magma in Pu'u'o'o started also to drop. So this was the situation that my colleagues started to face when at the beginning of May of 2018. So the sequence of events during this eruption goes like this. On May 2nd, the lava lake level begins to drop at Hele Mau crater, which is at the summit. And in the lower East Rift Zone, ground cracking appears. And then as the lava level drops, the onset of fissure eruptions, that is the lava flowing out of the fissure and flowing over ground. And that basically continued pretty much until the end of August. And during this time at the summit, the lava level kept dropping in the conduit. Eventually, it disappeared from view. And then later on, the crater, as the magma chamber started to empty out, the crater collapsed. So these are the main events during the Kilauea eruption in 2018. So here's a picture of the first fissure that opened up. And then eventually you end up with a big river of lava flowing down the hillside. So these are typically called effusive eruptions because the magma is not explosive. It comes out of the fissures and flow on land surface, although very destructive as well. However, there was another hazard, which is actually at the summit. So at the summit, here's a picture of the top of the volcanic conduit on May 6th. So remember, on May 1st, the lava level started to drop. So on May 6th, it dropped a significant amount. And by May 9th, this is the last picture that was taken where lava was actually visible. And then after that, the lava couldn't be seen anymore. So this was a hazard in the following sense. The general thinking was that if you have a caldera with a volcanic conduit filled with magma, so inside a volcano, there is also a water table. And this is the groundwater in here. Near the conduit, because it's so hot, basically you have steam in here. But as the lava level starts to drop, if it drops below the water table, at some point, water will be able to flow into the lava conduit. And at the same time, there are usually rock falls that could plug up the conduit. And if that happens and steam pressure builds up, then eventually you'll have a big explosion. And they call these steam explosions or phreatomagmatic explosions. So these are, explosions like this did happen in the history of Kilauea. And there are a couple that are very famous. So in 1790, there was a huge explosive eruption. 1790 is just about 10 years after James Cook reached Hawaii. So this is pre-European settling in Hawaii. In the 1920s, I think, a huge number of, like thousands of human footprints were found on this lapilli ash that was from this 1790 eruption. And by analyzing the size and of these footprints and where they're going, the conclusion was that this eruption killed a party of warriors and their families that were traveling close to the summit. And the fatality estimates range from about 80 to over 5,000. Another really well-known explosive eruption was in 1924. And this one was very well studied. And this became kind of this defined the thinking of how explosive eruption works at Kilauea. And the thinking by volcanologists who studied this eruption was that, as shown in the figures earlier, that as water flowed into the volcanic conduit and meets hot rocks and magma, it flashes into steam and generates a huge explosion. And this was written up by Harold Stearns in 1925, the year after the explosion. And this pretty much defines the thinking of how these explosions work. So obviously the USGS folks at the Hawaii Volcano Observatory was very worried about this possibly happening as the lava level dropped in the volcanic conduit. So my colleagues came to me. One of my area of specialty is numerical simulation. And they asked me to try to make some simulations to see if a similar kind of explosion could happen. So luckily, we have a computer model called hydrotherm, which can simulate fluid flow under very hot conditions, up to 1200 degrees C. So this became a very useful tool. And the questions that my colleagues wanted to know is, when will groundwater start to flow into the conduit? What will be the flow rate? And they want the answer as soon as possible. So, I got to work and set up this hydrotherm simulator. Now, there was not a lot known about the groundwater conditions in Kilauea, just because it's a difficult environment to drill wells and make measurements and things like that. So basically, the way to approach this type of problem is to make simulation runs using many different combinations of parameters, and then look at kind of the bounding result, what bounds the results. And basically, all this work had to be done in 3 or 4 days, because they need some information to determine how much to forecast in terms of hazards. So in this simulation, I simulated the problem in 2 stages. So we know that the magma chamber, or the magma conduit, was filled with magma for at least 10 years, from 2008 to 2018. And then as the eruption occurred and the magma was drained away, then you end up with an empty conduit. So this sets up kind of a 2-stage simulation, where the simulation starts in 2008. We have this would be like part of the volcano. We have the magma filled with the magma conduit filled with magma at 1,000 degrees C, which is kind of the typical temperature of these magma. And this would start heating the rock. And after 10 years, you will have a region of hot rock. We take away the magma and drop the temperature down to, we decided to use 90 degrees C as a representative temperature of, what the kind of air-filled empty conduit would be. And then see how long would it take for water to start flowing in. So I'll just show you like one typical series of simulations. And what I'm going to show is the saturation of water. So what this model simulates, one of the variables that the model simulates is how much water and how much steam is in each part of the volcano subsurface. So this is a picture of a slice of this volcano. The conduit wall is here, and then we go away from the conduit wall. The green color represents area that is saturated with water. So in this area, it's all liquid water. And the yellow area is area that is pure steam. And then, the gradation between would be a mixture. So for example, this color here would be 40% liquid water and 60% steam. So if you have a magma conduit that's filled with magma at time 0, after 1 year, basically the model suggests that maybe about 10 meters from the magma chamber, this region would be totally steam, and then outside would be liquid water, and there's a little bit of transition where there is partial water, partial steam. And then these arrows are flow directions of water, which is in black, and steam, which is in white. So after 10 years, the steam region is larger because the rock is continuously heating up around the magma conduit. So the air region of steam now extends up to maybe 30 meters from the edge of the conduit. And then beyond that, you have liquid water again. And again, the flow is actually away from the conduit because steam expands. So when the steam expands, it pushes the water away. Okay, so at this point, now we're at the start of the eruption. All the magma drains away, and we have a cool condition here at 90 degrees, and we want to see how fast water will start flowing back into the magma conduit. So we keep running the simulation. 1 year later, we still have a significant region of steam. So in this model then, even after 1 year from the drainage of the magma from the conduit, we still have basically a region of steam blocking water flowing into the conduit. After 2 years, I apologize, somehow the flow arrows got lost in this diagram. So, but anyway, we see that water could almost start to flow in at the bottom of the simulation region. There's still a wedge of steam in here. And after 3 years, you will have active water flowing in. So in this region, you will have a mixture of water and steam. So both water and steam would be flowing in. So we ran many of these simulations using different parameters. We didn't know exactly how wide the conduit is. There are many parameters such as permeability and porosity that varies in a volcano. And after making all those runs, we came to the conclusion, before I do that, so here's a picture of kind of the simulated steam and water inflow rate into the conduit, where this line is steam and this line is water. So at the beginning, right after the conduit was drained, you have steam flowing in, but no water. And since steam is already steam, it's not going to flash into steam. This suggests that the explosive potential would be very low. And it's only after 2 years when you have water starting to flow in this particular simulation. So we take all the different simulations and kind of bracket them. We end up with a graph that looks like this. So some simulations showed earlier inflow, maybe a few months, and much higher inflow rates. Some simulations shows a much later inflow, maybe after 2 years, and a smaller inflow rate. And then there are curves bracketed by these two. So this is kind of like, in climate modeling, where you have all these different climate models and they gave different projections. And then so you have this range of different projections. But based on this, we felt comfortable in concluding that you're not going to have water flowing into the lava conduit for at least a few months. So the conclusion is that the heating of the magma in the conduit from 10 years creates a region of very hot rocks surrounding the conduit. And even after the magma is drained, the region of hot rock would prevent liquid water from flowing into the conduit because it would just turn to steam. And so that was our conclusion that we presented to the Hawaii Volcanic Observatory. However, we do have to recognize that explosive eruptions can occur when rocks from the conduit wall falls into the magma, and that happened a number of times during the eruption. And so there, once in a while, there will be a big puff of smoke that comes out, but they are not as huge as these steam explosion that happened in 1790 or 1924. So as I mentioned, after the crater, after the magma chamber was drained, the crater started to collapse. So from end of April until beginning of August, the crater actually collapsed a huge amount, probably over 1,000 meters. And this is something that was daily filmed by cameras at the edge of the crater. And so every something like 30 hours, the crater flow would drop a little bit, and that kept happening. So here's a picture of the crater floor in 2008. So this was way before the collapse. And here is the Hawaii Volcano Observatory at the edge of the caldera. And for comparison, here is the picture of the collapsed caldera on August 1st. And here again is the now closed Hawaii Volcano Observatory. And it's a pretty dramatic comparison. So 1 year later in 2019, somebody flying over the caldera saw a little green patch. And if you zoom in, it looked like a little lake. So that got everybody excited because water is finally flowing into the caldera. And over the next, about 12 to 15 months, the size of the lake starts to grow and some more. And then sometime in late 2020, another eruption occurred. Magma came in and just basically boiled this lake away. But because of this presence of this lake, the volcanologist in Hawaii was able to estimate the inflow rate by measuring the lake volume. And so this gave kind of a rough test of our model. So when we ended up plotting our bracketed model prediction with the inflow rate that was actually measured from measuring the water level in the lake, it turned out that our bracket was, well, it was a pretty wide bracket, but at least it was reasonable. So what did we learn? Well, we learned that established long-held thinking can be improved upon because, it has been a long time since 1924 or 25 when, the original thinking of how eruptive explosion works in Kilauea. And I think using modern technologies such as computer modeling, we're able to improve on that. Always keeping in mind the famous saying that all models are wrong, but some are useful. So, there are many things during this eruption that the model didn't really simulate, such as the collapse of the crater. But in the end, the insight gained from doing this modeling provide useful information. And that's my presentation, and thank you very much.
Thank you, Paul. That's fascinating. If the lake hadn't appeared, how would you have validated the model, or is the lake the inevitable validation of when the water shows up?
I think we were, well, at least those of us who deal with groundwater and volcanoes was expecting a lake to show up eventually. And the fact that it showed up a little over a year afterwards was, reasonable, but we certainly couldn't have predicted it very well.
It sounds like it was right within your bracket. So
yes.
But why didn't the 2020 eruption cause a phreatic? What's the term? Why did it just boil the lake away as opposed to something more catastrophic?
I think because it was no longer in a conduit. It was like a big wide open area. So there was no way for, the eruption, the steam eruption model thinking is you have a narrow conduit that could have been plugged up by rocks falling into the conduit. And then it enables steam to build up. Whereas in a big open pit, if you have some water and the lava flows in, there was no way for the steam to kind of build up pressure before it explodes. So it just boiled away.
And maybe Andrew can comment on this, didn't we have a massive eruption of that sort in the Pacific some months ago?
The Hunga Tonga?
Yeah, is that a similar phenomena?
I mean, kind of. That was the magnetic conduit getting exposed to the ocean.
Okay.
So yes, it was steam.
It was steam. All right. So a couple of other questions from the chat. What is the translation for pu'uo'o?
Oh, I should know, but I don't. I'm sure we can look it up, but I'm sorry, I don't know the answer.
And also from Gary, how did the geologists in 1924 collect and analyze the data? And were there any geologist fatalities reported?
I am not aware of fatalities. I think the thinking was primarily qualitative rather than quantitative in the sense that the process makes sense, but at that time there just wasn't the technology to actually quantitatively calculate, how much water would be necessary and what rates of flow and things like that. So it was, just like in many theories in geology, you look at how rock layers bend or something like that, and you see it and it makes sense, but it's difficult to actually compute the stress changes that would require to, make those, to have all the variables add up correctly.
Another question from Wes in the chat. When the lake appeared in the crater, this is a good question, was that the actual top level of the water table?
Yes, that is. And in fact, we put together another model to simulate the lake rising. And that is indeed the top of the water level, or the water table.
I noticed that it changed color, or it appeared to change color over time. Does that represent the mineral composition, or is that just the refraction?
Probably. I mean, I've seen it green. I've seen it. It's probably a combination of the minerals in the water and, whether the sky is cloudy or blue.
Okay. I remember we took a trip there back in 2004, I think, and the thought of that crater being so much deeper is hard to comprehend. But were you present on the island during this, or were you doing your research from Menlo Park?
I was in Menlo Park.
I see.
Yeah.
If anyone else has a question and either wants to jump in on the chat or vocally, Andrew is waving his hand.
Yeah, I don't know if you're familiar with this, but how did this eruption affect the steam vents around the Kilauea summit area?
I don't know. I can ask my colleagues. I mean, I would think that as the lava drained away, then might possibly be less steam. But then, in 2011, the magma came back. So maybe temporarily there was less steam, but I don't know for sure.
It's all very interesting. Thank you.
Well, where else has your work with you? Where else did your work in hydrology with USGS take you? If that question makes any sense.
Well, I did a study of the Spokane Valley Rathdrum Prairie Aquifer, which is half of it is in Washington and half in Idaho, near. So I'm a little bit familiar with that area. I ended up working on the Deepwater Horizon oil spill during that period, again, because, my specialty was modeling and they need somebody to do modeling. And hazardous waste sites in eastern United States, various places.
Yeah. Well, we really appreciate your taking the time. Hopefully someday we'll get to meet you in person, perhaps here in the Northwest, or when we travel down to California, or perhaps we never will, but we'll see you here, and we're grateful for your contribution. So unless there's another question, we're right at the top of the hour, so I'll have Gary turn off the recording.